you can actually find a closed form formula for the coefficients.
Okay.
So that is this x times x transpose inverse times x transpose times y.
Right.
So that gives, but in when you have large data sets, that's matrix X. The number of rows in that is fairly large. So if you have lots of variables and lots of data, then inverting this matrix becomes pretty difficult to handle. But for small ones, you can do it. I mean, that's.
Right.
Yeah.
So I think that when people do optimized, you know, linear models for really, as Neil was saying, for, you know, lots of variables, and, you know, said part of it is you have X transpose with whatever inverse.
Right.
So the inverse, how do you do that?
Yeah.
So when you do that, frequently people will use gradient descent to approximately compute the inverse, or at least to find the determinant. So you can actually wind up using gradient descent in linear models in that way. I mean, there is a closed form solution, but you know, I'm told that for, you know, huge systems of linear equations, you know, and obviously there's an exact solution, but people use gradient descent to solve them. It's just faster.
Yeah. No.
Yeah. So there's a possibility that when we say that matrix is singular and it cannot be inverted, we can still use gradient descent to find coefficients and still do linear regression.
Yeah, you can. I mean, as we saw, it's a matter of sometimes they don't converge, but in the linear regression, I mean, it can happen. Yeah, it can happen that if there are variables that are very highly correlated or multiples of each other, so that matrix will become singular, and then you can't invert it. But I don't know if I honestly don't know what you get if you do that. If you get anything useful.
Okay. Yeah. So when we get to when we talk about that linear regression, as you mentioned, like about the correlated variables can make the matrix singular and inversion difficult. That is one question I have. It's kind of a practical question. Like you have 100 variables. Let's say 100 variables in a regression, and now a priori you have no idea which of these variables are correlated.
Right.
Now, what is the best method to make these, to come up with you can do PCA probably, but other than PCA, what can be other way of reducing the number of variables so that you have independent predictors and then do regression on that? There seems to be no simple method.
Well,
stay
tuned for this lecture.
Okay, all right, so let's start.
You can definitely do some. I mean, there are tricks where you can make if you use regularization, then you can make the matrix invertible. But then regularization can also tell you which variables you can that you can throw out or even that becomes zero when you do the regularization.
Okay. So depending on what kind of regularization.
Yeah, right. Yeah. So I think Adam will talk about the lasso.
Okay.
But just to give an advertisement, one of the problems is if you have highly correlated variables, that means your matrix is invertible, but the determinant is really small. And, you know, so you have to get this inverse. And the inverse of a very small number is a very large number. Right. So very, very small errors in your, or differences in your observations can lead to very large differences in what your actual coefficients are, you know, which is very unstable. I mean, if I have a data set that's 1, 1.1, 1.2, and I get out a coefficient of 3, and then I have 1, 1.1, 1.21, and I get a coefficient of 1,000,000, that's you know, that kind of numerical instability is no good. And one of the things regularization will do is it'll force it absolutely will force the coefficients not to be too large. So regularization is the way to deal with these things.
Okay,
and
so I think
will actually even go so far as to say get rid of these variables.
Okay, so I think this will be very interesting because I know of lasso and ridge, but I'll see like how exactly it can be used to get around this problem.
Yeah, it makes the matrices invertible. That's the.
But first,
we will talk about something else.
Okay.
let's share your screen.
Or we'll talk about. We should share the screen. All right, is it viewable?
Yes.
Okay, very good.